Now let's talk about a really useful theorem for factoring polynomials and finding their roots. It's called the rational roots theorem. And this is meant to go in conjunction with the previous video using the remainder theorem. So before we jump into the rational roots theorem, I want to go over some vocabulary just so you understand the similarities between finding a root and finding a factor. So if, like in the last lesson, x minus c is a factor of f of x, then we can say a bunch of things about it. For starters, we can say that the remainder of f of x divided by x minus c will be 0. The second thing that we can say is, it turns out that when you plug in x equals c into f of x, you get 0. So if you take x equals c and you plug it into f of x, you will get 0. That's really important. That means that x equals c is an x-intercept, assuming that it's a real number, for the graph of f of x. And we have a lot of words for x-intercept. X-intercepts are called roots, and they're also called zeros because they make the function equal to 0. So whenever you're reading in your textbook or studying along with these videos or doing your homework, all of these following things mean the same. All of these things mean the same thing. If a number is an x-intercept, that's the same thing as a 0. Notice c itself doesn't have to be 0. It just gives us a 0 value when we plug it into the function. So an x-intercept is the same as a 0, is the same as a root, which is what we're talking about in this section. And that's the same thing as saying that x minus c is a factor. So as a really quick example, in the previous lesson, we found out that x minus 2 is a factor of something simple, x squared plus x minus 6. That means that the remainder, after we divided x squared plus x minus 6 over x minus 2, that remainder was 0. That also means that when you take x equals 2 and you plug it in, if I call this f of x, you plug it into that function, 2 squared plus 2 minus 6, you'll get 0. That also means that x equals 2 is an x-intercept. That also means that it is a root. Let me change this. That also means that we could call it a 0. So a root, a 0, an x-intercept are all the same, meaning that they mean the same thing, assuming that we're talking about real numbers. And that means that x minus that number is a factor. So factors, roots, x-intercepts, zeros, they're really, really, really closely related to each other. Okay, let's talk about the rational roots theorem. So the rational roots theorem says this. If you have a polynomial, so let me do a polynomial like this one. Say you have the polynomial f of x equals x cubed minus x squared minus 17x minus 15. And we were to try to find all of the roots, rational roots, so rational meaning not an imaginary number and not a square root that doesn't simplify. If we were to find all of the rational roots or x-intercepts or factor it, however you want to look at it for this, they're all of the same format. All of the possible rational roots have the same format. They are positive or negative p over q, where p is any number that divides into 15 evenly. Whoops, let's make that a highlighter. There we go. So that divides into that last number evenly. And q is any number that divides into, in this case, 1 evenly. And 1, I did it again, 1 comes from the coefficient here in front of the first term. So here's what that means for this problem. All of our, and an important word here, by the way, is the word possible. All of our possible rational roots or rational zeros would be of the form plus or minus, let's see, what goes into 15? 1 certainly goes into 15. 3 goes into 15. 5 goes into 15. And 15 goes into 15. And thankfully, the only numbers that go into 1 in green here are 1 and 1. So here's how this could look. Plus or minus 1, 3, 5, 15. So all of our possible rational zeros or rational roots for that polynomial are contained in this list here. Now we certainly don't have, 2, 4, 6, 8 different roots, but all of the possibilities are listed there. Let's do another example before we start to actually find which ones work and which ones don't, and we'll come back to this one. So let's say f of x is equal to 2x cubed minus 4x squared minus 14x plus 28. Now all of our possible rational zeros or roots are positive or negative. Let's see, I need everybody that could possibly go into 28. So that would go on the top. Whoops. So the numbers, let's see, the numbers that go into 28, 1, 2, 3 doesn't go in, 4 goes in, 5 doesn't go into 28, 6 doesn't go into 28, but 7 does. 8, 9, 10, 11, 12, 13 do not go in, but 14 certainly does. And 28. So those are all the possible numbers that divide in evenly to 28. Those would be in the numerator. The numbers in the denominator would be all of the numbers that go into 2. So let me make that go away and get my highlighter back. And thank goodness that's a short list. All the possible numbers that go into 2. 1 goes into 2 and 2 goes into 2. So the ways to write this are plus or minus. I'm going to write, instead of writing it like I did up here, plus or minus 1, plus or minus 3, I'm just going to write the plus or minus in the front and then list all of them. So this will be plus or minus 1 over 1, 2 over 1, 4 over 1, 7 over 1, 14 over 1, and 28 over 1. But then I also have the possibility of, 1 over 2 in the denominator. So 1 over 2 in the denominator. Now 2 over 2 in the denominator, I don't need to write. 2 over 2 is already listed, because 2 over 2 is the same thing as 1, so it's a repeat. But let's see, 4 over 2, same thing. 4 over 2 is already listed. 4 over 2 is 2. That's a repeat. 7 over 2 is not. 14 over 2 is listed. That's the 7. And 28 over 2 is listed. That's the 14. So now I have my complete list of all the possible rational zeros for that polynomial. Okay, let's use the list that we came up with for that first example to go further, and we will find all of the rational zeros, not the possible ones, the ones that actually work for that polynomial f of x. So here's what we're going to do. We're going to put together this video, this concept we've just done, and the previous one where we checked for remainder equal to 0. So we're not going to randomly pick x values and use synthetic division. In this case, we're going to only pick from the list of all possibilities. And a natural place to start is with x equals 1. So I'm going to pick my first value here, x equals 1, and I'm going to check if this is a 0 or a root. Okay, so remember, if x equals 1 is a 0, that's the same thing as saying x equals 1. X minus 1 is equal to 0, so x minus 1 is a factor. So let's check this. So I'm going to put 1 up in the synthetic division box. The numbers that I'm looking for the division come from f of x. So those coefficients are 1, -1, -17, -15. And I'm going to do synthetic division, and I'm going to hope that I get remainder 0. If I do get remainder 0, x equals 1 is a 0. If I do not get remainder 0, then x equals 1 is not a 0. So let's go through. Bring down the 1. 1 times 1 is 1. -1 plus 1 is 0. 0 times 1 is 1. -17 plus 1 is -16. And -16 times 1 is -16. This is not looking good. -15 plus -16 is -31. And remember, this is our remainder. It's not 0, which means that x equals 1 is not a 0. So I can eliminate my x equals 1. And I have to be careful, actually, with the way that I just wrote that. I can't forget that x equals -1 is a possibility. So before you cross those out, it might be a good idea to cross out just the positive in front of it. So the next natural one to try is to check if x equals -1 is a 0. So let's do that. 1, -1, -17, -15. And start the synthetic division by bringing down the first number. -1 times +1 is -1. -1 plus -1 is -2. -1 times -2 is 2. -17 plus 2 is -15. And -1 times -15, oh, this is great, is +15. When I add them together, I get 0, which is our remainder favorite number. That means that x equals -1 is, yes, it's one of our rational roots, one of our rational zeros. So there will be probably 3 rational zeros here. Three zeros here, but they don't all have to be rational. Some of them could be imaginary, some of them could be square roots. So there's 2 things that we could do right now. We could keep going. We could keep checking 3 and plus or minus 5 and plus or minus 15. By the way, just because you get one yes for -1 doesn't mean it won't work a second time. You could try that again. But here's something I want to show you to save yourself a little bit of time. Remember in the last video, we just found out that f of x can be factored to x plus 1, coming from the x minus the -1, times x squared minus 2x minus 15. I'm going to clean that up just a little bit. Once we get down to having 3 terms here, when we get a remainder 0, this quadratic is something we should all be pretty comfortable with. We can hopefully factor it, and if we can't factor it, we could use the quadratic formula to solve for the x's. This one in particular factors pretty nicely. Factors to, let's see, 3 and 5, so x minus 5 and x plus 3. So there's a fully factored version of f of x, and its zeros, or its roots, or its x-intercepts, whatever you want to call them, are -1, +5, and -3. One last thing I want you to notice before we move on to another example is that, let's see, let me do this. -1, +5, and -3. -1, +5, and -3. Since they're rational numbers, they are all included in our list of rational roots. We would never have x equals 2 as a rational root for this problem because it didn't show up in this list here. These take a lot of practice, so let's do another example. Let's now do the example to find all rational zeros for f of x equals, let's do x to the 4th. I'm going to move this, hold on. Oops, move it over just a little bit. Sorry about that, thank you. X to the 4th plus x to the 3rd minus 11x squared minus 9x plus 18. Okay, so the first step to doing these, step 1, list all of your possibilities. List all your possible rational zeros. So for that, this will be the possibilities plus or minus. I'm going to write it in this terrible format here. Remember, we want to start with all of the possible numbers that go into 18 in the numerator. So those would go up here. And those numbers are definitely, whoa, that's not a pen. 1, 2, 3 all go into 18. 4 does not, 5 does not, but 6 certainly does. 7 and 8 do not, but 9 does. And 10, 11, 12, 13, 14, 15, 16, nothing up until 18. So that's a list of all my possible numbers that divide into 18. Fortunately, this one is kind to us in the denominator, all the possible numbers that go into the leading coefficient, which in this case is just a 1 again. So that could only be 1. Okay, so all of our possibilities that possible rational zeros we could have are plus or minus 1, 2, 3, 6, 9, or 18. Okay, once you get your list of possibilities, step 2 is to use synthetic division to check and see which ones in the above list give us remainder 0. Now, this can take a long time. Be nice to yourself and start at the beginning. So let's start with x equals 1. So we're going to check x equals 1. And again, the polynomial you're using for your synthetic division is f of x. So 1x to the 4th, 1x squared minus, 1x cubed minus 11x squared minus 9x and positive 18. We'll do a quick round of synthetic division. Bring down the 1. 1 times 1 is 1. 1 plus 1 is 2. 1 times 2 is 2. Negative 9. Negative 9. Oh, this is great. Negative 18. Negative 18. 0. Yay! Once we get a remainder 0, we know that 1 is a yes. Okay. We need to keep going. And this right here, 1, 2, negative 9, negative 18, there's good news and bad news about it. The good news is that it has 4 terms and it factors. The bad news is, you might not remember how to factor it. So I'm going to pretend that you don't notice that that polynomial factors still. What you can do is you can take, we call this the depressed polynomial. It's not a sad term. It's the depressed polynomial. You can only use these depressed polynomials when you get a remainder 0. But now instead of using the really big 1, 1, negative 11, negative 9, and 18, instead of using that and doing synthetic division to find the rest of the rational zeros, we can use the depressed version instead. It's not wrong to use the bigger one, it just is a lot easier to use the smaller one. So when I go to check another one, because we should have probably 4 total. When I go to check another one, say x equals 2. I'm going to check x equals 2 with the depressed polynomial 1, 2, negative 9, negative 18. And if I have remainder 0 here, I would have remainder 0 for the big f of x. So let's try this. Bring the 1 down. 2 times 1 is 2. 2 plus 2 is 4. 8, negative 1. Ooh, this doesn't look good. Negative 2. So we get negative 20, which is a no. So let's check x equals negative 2. So negative 2, I'm going to go 1, 2, negative 9, negative 18. Bring down the 1, multiply by negative 2, 0. Multiply by negative 2, 0. Negative 9, and negative 2 times negative 9 is positive 18, which gives us a 0. Great. Now we also are down to 3 terms, 1, 0, negative 9. So here's what that tells us. F of x factors to x minus 1 from here. And it factors to x plus 2 from here. And furthermore, it factors to x squared minus 9 from that further depressed polynomial. So the first one in green told us that x minus 1 is a factor. The second one in yellow told us that x plus 2 was a factor, and its depressed polynomial that's left over is x squared minus 9, which hopefully we all know how to factor. So you can keep doing synthetic division, or you can factor it. We've got x minus 1 and x plus 2 from all our hard work before, and now we have x plus 3 and x minus 3. So depending on what the question is asking you to do, if you need to factor f of x, there's the factored version. And if you want your zeros, 1, -2, -3, and +3 are your zeros. And one last time I want to point out, 1, -2, -3, and +3, these zeros came from 1, -2, and ±3 came from our list of possible rational zeros. Let's do one last example before you practice some on your own. One more example. Let's do f of x equals 2x to the 5th minus 7x to the 4th minus 10x cubed plus 17x squared plus 26x plus 8. Whew. Huge. Okay, and I won't write the directions out. They're exactly the same as the last few. We're going to find all of the rational zeros, and we're going to factor it completely. So step 1, let's list all of our possible rational roots. That will be my shorthand for rational roots. So plus or minus, let's see, all the factors that go into 8. That would be 1, 2, 4, and 8. Over all of the factors that go into 2. Well, that's just 1 and 2. So all the different ways to write that would be plus or minus 1, 2, 4, and 8 all over 1. And then plus or minus 1 over 2, 2 over 2, well, we already have that listed, 2 over 2 is 1. 4 over 2, we have listed as 2. And 8 over 2, we already have listed as 4. So including the 1/2, there's our complete list of possibilities. And the next, we're going to use synthetic division to figure out which of those actually work. So let's start with 1. So for 1, we have 2, -7, -10, 17, 26, and 8. Ooh, makes me glad for synthetic division. Bring down the 2. 1 times 2 is 2. -7 plus 2 is -5. 1 times -5 is -5. Add those two, -15. Multiply by the 1, -15. Add to 17, we get 2. Multiply by the 1, we get 2. Uh-oh, this isn't looking good. 26 plus 2 is 28. And 1 times 28 is 28. When we add it to 8, we're going to get 36, which is not good. It's not equal to 0. So x equals 1 is not a possibility. X equals -1. Let's see, -1. So one thing to point out, I cannot use this version here as a depressed polynomial because I didn't get remainder 0. So we're going to have to go back to the original. So 2, -7, -10, 17, 26, and 8. Okay, bring down the 2. -1 times 2 is -2. -7, -2 is -9. -9 times -1 is +9. Plus -10, -1. -1 times -1 is 1. 17 plus 1 is 18. 18 times -1 is -18. Oh, I'm hopeful. 26 minus 18 is 8. And 8 times -1 is -8, which is a 0. Yay. Great news. Not only did we find one of our zeros, but now we can start using the depressed polynomial that's just at least a little bit shorter to check more possibilities. Now, I really should be checking x equals -1 again. Once you get a yes, you should check to see if it isn't a yes twice. But in the interest of time, I'm going to check x equals 2 instead. So 2, -9, -1, 18, and 8. That is still too big for me to try to factor. Bring down the 2 and start multiplying by the number in the box. So 2 times 2 is 4, plus negative 9 is negative 5. Times 2 is negative 10. Negative 1, negative 10 is negative 11. Times 2 is negative 22. We'll add 18 and negative 22. We get negative 4. Oh, this is looking great. 2 times negative 4 is negative 8, which gives a remainder 0 again. Every time you get a remainder 0, 2 great things happen. Yes, you find another, let me highlight these, solution, or 0, but you can also start using the depressed polynomial, which is smaller. So we'll start using these smaller ones. Okay, so let's see. I don't see, it has 4 terms and I know how to group, but I don't see how more are going to group. So let's keep going. 2, negative 5, negative 11, negative 4. Let's check x equals negative 2. Whoops, I don't want to write it that way. Let's check x equals negative, negative 2. And I'm going to put negative 2 in the box. So bring down the 2, multiply by negative 2, get negative 4. Add it to the negative 5, get negative 9. Multiply that by negative 2, we get positive 18. 18 minus 11 is 7. That's not looking good. Negative 14. Too bad. We were on such a roll. So let's check x equals 3. No, we would not check x equals 3. X equals 3 is not in our list of possibilities. So let's go to x equals 4. Let's go to x equals 4. Okay, so we check x equals 4. 2, negative 5, negative 11, and negative 4. Bring down the 2. Multiply by 4 to get 8. Plus negative 5 is 3. 4 times 3 is 12. Plus negative 11 is 1. And 4 times 1 is 4. Plus negative 4 is 0. So close. Okay. Now by this point in the problem, you're probably pretty sick of doing long division. So we just found 3 of probably 5 rational zeros. We could keep going, or we could factor 2x squared plus 3x plus 1, our newest depressed polynomial. So I'm going to go back, erase some of this stuff from before to give us some room on this page. And I'm going to do that. So let's clear this off over here. There we go. Okay. So 2x squared plus 3x plus 1 factors to 2x plus 1 and x plus 1. So that means that we have the factored version of f of x is x plus 1 from here, x minus 2 from here, x minus 4 from here. Let me clear up a little bit more room. Oh, and this is quite messy. So I apologize. Let's see, we had x minus 4, 2x plus 1, and x plus 1. We just learned a very, very valuable lesson. Do you see how x plus 1 showed up again? It showed up twice. In the very, very first one that we found, and again when we factored it. We could have saved ourselves a lot of time if we had checked x equals negative 1 a second time. It wasn't the end of the world, but it did take us a while to do this problem. It showed up twice. It would have saved us a lot of time if we had just checked that one more time on this polynomial down here. Nonetheless, we still got our answer. So we have, this is our factored version, or you could write x plus 1 squared, x minus 2, x minus 4, and 2x plus 1 is the factored version of f of x. And the zeros are -1, +2, +4. And if we set 2x plus 1 equal to 0, that gives us -1 divided by 2. And I know I've erased it, but if you look back at your list of possible rational zeros, all of those numbers, -1, 2, 4, and -1/2, are all listed in our possible rational zeros.